Hello everyone, welcome back to MP Coding's Linux device driver development series with Raspberry Pi. In the last two videos, we discussed wait queues and the poll mechanisms. Today, we will discuss asynchronous notification using fasync. Okay, in the previous examples, we covered two ways a process can wait for data from a device. First, blocking read. The process calls read and sleeps inside the driver until data arrives. Second, poll and select. The process waits in user space, monitoring one or more file descriptors. When one becomes ready, it wakes up and then calls read. In both cases, the user space application is still waiting. It is blocked until the device becomes ready, so it cannot continue doing other work in the normal flow. Async notification using fasync is different. Here, the process registers its interest in the device and then continues running normally. It does not sit in a blocking read, and it does not stay inside a poll loop waiting. In our example, when the button is pressed, the kernel sends a SIGIO signal to the process. That signal interrupts whatever the process is currently doing, and then the signal handler in user space can call read to fetch the data from the driver. So compared to blocking read, poll, and select, this is a more asynchronous model. You can think of it like this. In blocking read, the process sleeps inside the driver. In poll/select, the process sleeps in the kernel's polling infrastructure waiting for an event. In fasync, the process does not wait in either place. It keeps running, and the kernel notifies it asynchronously using a signal when data is ready. This is one of the simplest asynchronous I/O mechanisms available in Linux, especially for character drivers. Okay, let's go to the implementation. Here in the module source file, I am starting from almost the same code we used in the previous examples. But for this version, I removed the poll implementation and also removed the wait queue logic, because for async notification we do not need those mechanisms. Right now, when the button is pressed, the ISR simply prints a message to the kernel log. The open and release file operations are still very simple. They just print messages when the device is opened and closed. And the read function only copies the message buffer to user space. The init and exit functions are not changed. So currently, this is just the base driver, and now we will extend it to support async notification with fasync. First, open the file_operations structure definition. Here we can see that the kernel provides fasync file operation callback. This callback is used when user space enables or disables asynchronous notification for a file descriptor. So let's copy this definition and add it to our driver. I will declare it as a static function and name it my_fasync. The first parameter is the file descriptor number from user space. The second parameter is the driver's file structure pointer. The third parameter is called on, and it tells the kernel whether to enable or disable asynchronous notification for this file descriptor. This value is actually controlled from user space, and I will show how that works later. Inside this function, I will first add a kernel log message to indicate that the fasync callback was called. Then we call the helper function provided by the kernel, called fasync_helper. This helper function automatically adds or removes the file descriptor from the asynchronous notification list. For this function, we need to pass the file descriptor number fd, the file pointer, the on parameter, and finally a double pointer to async_struct. So first, we need to declare a pointer to this structure at the top of the driver. Static struct fasync_struct pointer. I will name it as async_q. This pointer will store the linked list of processes that registered for asynchronous notifications. Let's pass the address of async_q because fasync_helper expects a double pointer. The helper function returns an integer value, and we simply return that value from our my_fasync function. Now let's understand what the on parameter means. I created a small table to explain how it works. If the value of on is 1, it means Add this file descriptor to the async queue. If the value is 0, remove this file descriptor from the async queue. If the value is -1, force removal, which is usually used during cleanup. Because of this, we must always make sure to remove the file descriptor from the async queue when the device is closed. Otherwise, if the process exits without clearing the O_async flag, the kernel may still try to send signals to an invalid file descriptor. That can lead to a use-after-free bug and potentially crash the kernel. So inside the release function, we explicitly remove the file descriptor from the async queue. Now, you might be wondering why we pass -1 as the file descriptor in here. The reason is that during release, the user space file descriptor is no longer valid or relevant. At this stage, we are not adding or updating anything. We are simply forcing the removal of this file from the async notification list. When we pass -1, it tells fasync_helper that this is a cleanup operation, not a normal enable or disable request from user space. So instead of relying on the file descriptor value, the kernel uses the file pointer to identify and remove the correct entry from the async queue. This is important because if we don't explicitly remove it here, the kernel might still try to send SIGIO to a process that has already closed the device, which can lead to a use-after-free bug or even a kernel crash. Next, don't forget to register this callback in the file_operation structure. .fasync equals my_fasync. Now let's move to the interrupt service routine. When the button is pressed, we want to send a signal to all processes that registered for asynchronous notifications. To do that, the kernel provides a function called kill_fasync. This function sends a signal to all processes in the async queue. For this function, we need to pass the address of the async queue, the signal type, and a poll event value. Here I will use the SIGIO signal, which is the standard signal used for asynchronous I/O notifications. If you open signal.h, you can see many different signals defined in the Linux kernel. The last parameter indicates the type of event, so I will use poll_in, which means data is available for reading. If we look at the signal.h header again, we can see other poll events that we can use. In this example, I just simply use poll_in. Okay, to indicate that data is available, I will reuse the same simple logic we used in earlier examples. I will create a global variable called data_available, initialized to 0. When the button interrupt occurs, we set it to 1, and then notify the registered processes. Finally, we update the read operation. Inside read, we first check whether data is available. If no data is available, we simply return -e again, which tells user space that the device currently has no data. If data is available, we copy the message to user space. Here, I reset the data_available back to 0. This ensures that each button press generates only one read event. So after the data is read once, the device will again report no data available until the next interrupt occurs. That's it for the driver-side implementation. Now let's build the module. As you can see, the build completed successfully. Next, let's move to the user space application. Here, I have created a test application file. Right now, it is very simple. It just opens the device file and then closes it, similar to what we did in the previous examples. Now we will extend this application to enable asynchronous notification and handle SIGIO signals from the driver. After opening the file descriptor, we need to register a signal handler, so the user space application gets notified when the driver sends a SIGIO. So first, I will create a callback function, static void SIGIO_handler. This function must take one parameter, which is the signal number. Inside this handler, I will read data from the device. For that, I create a local buffer of 64 bytes to store the message coming from the kernel. Then I call read. Now, since the file descriptor fd is inside main, let's convert it into a global variable so it can be accessed inside the signal handler. Okay, now update the read. After reading the data, let's print it to the console. Terminate the null character and the print message. I will print SIGIO, button pressed, received, then the message from kernel. And I also call flush and pass std out to immediately flush the output buffer. Otherwise, sometimes the message may not appear instantly due to buffering. So the idea is, when the button is pressed, ISR runs, kernel sends SIGIO. This handler gets triggered and we call read from user space. Now the callback is ready. Next, inside the main function, first, need to register the signal handler using the signal function. For that, we need to include the signal.h header to use signal APIs. So here, pass the signal, in this case SIGIO. Next, signal handler, which is our SIGIO_handler. This is the step 1, to install the SIGIO signal to the signal handler. Then, we need to tell the kernel which process should receive the SIGIO signal. So we use file control and pass fd, and then f_set_own, which used to tell the kernel which process should receive the SIGIO signal for this file descriptor. Then next we pass process ID. Get PID returns the process ID of the current application. So the signal is delivered to the current process. So this tells the kernel, send SIGIO signals for this file descriptor to this process. Next, we need to enable asynchronous notification. First, I get the current file status flags using file control and pass the f_getFL. This f_getFL used to retrieve the current file status flags of the file descriptor. This is important because we don't want to overwrite existing flags. We just want to add a new one. Then, let's set the new flags. File control and pass the fd and f_setFL to tell update the file status flags. Then pass the current flags with o_async flag to enable signal-driven I/O. So this tells the kernel, whenever data is available on this fd, send a SIGIO signal. Now async notification is fully enabled. Finally, let's add the main loop. This loop represents the process doing its own independent work. Inside the loop, just print the message, working. Then I will print the counter value that increases every iteration. Here, create this counter variable and initialize it to 0. Then after every print, let's flush the output buffer. Then set 1 second sleep, just to simulate real work. Next, before going to the loop, I will print messages to indicate what has happened. Okay, that's it for the test application. Let's build it using GCC. In the terminal, type gcc space test_fasync.c space -o, then output file name, I just give test. Okay, build was successful. The test executable was created. Now I will open the kernel log in another terminal. Now first, load the module. Sudo insmod my_f async ko and hit enter. You can see the module is loaded and the device node is created at /dev/my_cdev0. Now let's run the test application and pass /dev/my_cdev0 as the argument. You can see on the driver's side, the device is opened and fasync is called. And on the user side, the test application is running, printing a counter value every second. Now let's press the button. When we press the button, the ISR is triggered. It sends the SIGIO signal to the registered file descriptor. In the user application, the SIGIO_handler is invoked. Then it calls read. Now in the driver's side, my_read is called. The data_available is 1, so message copy to user space. And it gets printed on the console, hello from kernel. You can see now, no waiting on either the device side or the user side. We simply send a signal and trigger the handler. Now if I press Ctrl+C, the loop is interrupted and the application exits. Before closing the file, you can see again the 2f async called. That is because, when the process exits, the kernel automatically clears the o_async flag, which triggers the .f async callback to remove the fd from the async queue. And additionally, in our .release function, we explicitly call my_f async to ensure proper cleanup. So these f async called are one from the kernel cleanup, one from our manual cleanup. This guarantees the async queue is cleaned safely. This is how we use asynchronous notification using fasync. A process using async notification does not need to wait in a wait queue at all. It simply continues running and gets interrupted by a signal when an event occurs. All the notes and other explanations are in the README file. Feel free to look at that also. Technically, we can also send signals to user space without using fasync, and I will cover that under advanced topics, sending signals to user space. Today, we focused on how to use fasync for async notification. So, in the next video, we will start kernel synchronization techniques. So stay tuned. Please like, share, comment, and subscribe to the channel. If you'd like to support my work or connect with me and give suggestions for future tutorials, feel free to check my social links in the description. See you in the next video.